Okay, let us begin. Yeah, so we are proving the deduction theorem and we have already proved one side implication. That was very easy. Yeah, we are proving the back side. So the purpose of deduction theorem is to allow transfer of formulas between left and right side with a single turnstile operator. Yeah, it's a deduction operator, proof operator. So if there is a proof of S implies T from capital S, then we also have a proof of T from S union singleton small s. That part we have seen. Now we are looking at the converse. So suppose you have a proof of T from S union singleton S. So now that proof is a finite length proof. So for that finite length proof, for each line we are going to replace that line inductively, of course, by a finite number of lines, so that the left hand side of the new proof always contains capital S as the left hand side. Yeah, so that's what we are going to do. It will be only S, and whenever we are replacing one line with something appropriate, then at the end, so if the line is, let's say, S union singleton S proves Ti, then at the end we always need S proves S implies Ti. Yeah, that's our goal. Now the first base case, there are two base cases. Now how do you decide what is base case, what is inductive case? What could be the reasoning of an unfounded line, like the line which doesn't depend on anything previous? It can either be a logical axiom or it can be a non-logical axiom. So that's how we determine what is a base case. What could be line number 1? What could be the reason for line number 1? Line numbers 1 and 2 always have to be LAs and NLAs, but line number 3 onwards they could have reason MP, modus ponens. So right now we already covered this base case 1. If the reasoning for line number I is S union is LA. Yeah, so here actually I should write here. So by monotonicity and LA we can conclude Ti from capital S, then this is LA1, and from that by using MP we can get this. Now let us consider base case 2, that line I has Ti as the right hand side and the reason is NLA. Now what could happen, tell me, if the reason is NLA, then Ti is in capital S or Ti is equal to small s, not in small s. Okay, so now subcase 1. So Ti belongs to S. Then here I am just going to write that proceed as above, then S proves Ti, NLA, and proceed as above. Yeah, there is nothing different happening. You just change the reasoning of this line, then LA1 is still valid and MP is still valid. Okay, so now subcase 2 is more interesting. Subcase 2, that Ti is equal to little s. Yeah, Ti belongs to curly bracket singleton S. So Ti is equal to S. So what do we want to prove? Tell me. We want to prove that capital S proves S implies S. How do we obtain that?
Ti is S, so S implies T is tautology.
S implies T is tautology. Yes, but it doesn't mean, even if it is a tautology, it doesn't mean that you already have a proof for it. See, we need to show, we need the sequent S proves, S implies Ti, but Ti is S. Okay, how do we obtain this? If you remember something from last lecture, so if I hide this part, then it is a tautology. Yeah, I mean S implies S is a tautology. So we have a proof of S implies S for every S. What is that called? We called it lemma 1. Right? So, yeah, so we use monotonicity. Yeah, why do we need to use monotonicity? Because when we proved that, we did not have any left hand side. Left hand side was empty. Right? So you can replace the left hand side by capital S with lemma 1 to obtain this. So lemma 1 gives you a 5-line proof of S implies S, and then you simply use monotonicity so that you can replace the left hand side by capital S, and you are done. Any questions so far? Let's proceed. So now we are done with all the base cases. So now we only need to show the inductive case. Okay, so for the inductive case, let's write it down. Suppose all lines with numbers less than k have already been converted, have already been replaced by finite, what word did we use? Finitely many lines, with finitely many lines. Okay, by finitely many lines with capital S on the LHS. And the reason for line K is MP. Then line K is what? S union singleton S proves Tk MP. Okay, but it has to be MP on some ij. Right? So what would be line I? Then without loss of generality, assume that line I is S union singleton S proves Ti, and line J is S union singleton S proves what? We cannot say Tj. Yeah, I mean that's where we had to make a choice. I said without loss of generality. Either line I would be something implies something, or line J would be something implies Tk. Yeah, I mean one of them has to be something implies Tk. Either Tj implies Tk or Ti implies Tk. So here we are going to say Ti implies Tk. So by induction hypothesis, since I and J are less than K, so yeah, one more thing, look at the first line that I have written. What did I say? Suppose all lines with numbers less than K. So what kind of induction are we using? Strong induction. Yeah, this is not weak induction. But anyway, strong and weak induction are equivalent. Okay. So by induction hypothesis, since I and j are less than k, in the new proof, we have sequence. What sequence do we have? We have sequence S proves S implies Ti and S proves S implies Ti implies Tk. Yes, I mean the proof for line I was replaced by finitely many lines, and the final one of those lines is S proves S implies Ti, and this is S proves S implies Ti implies Tk. Now tell me how to obtain a proof of S implies Tk. MP. I cannot use MP on this. Can you see that? Distributivity, self-distributive law. Okay. So add lines. So S proves that S implies Ti implies Tk implies S implies Ti implies S implies Tk. And what is the reason for this line? LA2 and don't forget monotonicity. I mean LA2, yeah, I think for LAs we don't need to write monotonicity. We can just write LA2. Then now I can use MP. Yes, so the first part of the implication is precisely given. So then S implies Ti implies S implies Tk. Yeah, the reason is MP on the previous two lines, and then once again I can use MP because S implies Ti. We already have a proof over here. So therefore, literal S implies Tk by using reason MP. Yeah? Are we done? We still need to argue since the last sequent in the proof of S had T in the RHS, by induction we have replaced it with a sequent S proves S implies T, and thus we are done. Yeah, this last line is also equally important, because what did we want to show? We wanted to show that capital S proves small s implies T. And because that was the last line, and because we have converted every single line, we have also converted the last line. So therefore we have this sequent as we need, and until then everywhere the left hand side was capital S. So we have actually obtained a proof of little s implies T from capital S.